Here's a sample electricity bill. And if we zoom in, no matter who your provider is, generally speaking, every electricity bill will have some indication of your usage measured in kilowatt hours. That's what you're paying for when you pay for electricity. So you're paying for some amount of kilowatt hours of electricity. Now, let's think about what that means. A kilowatt hour is 1,000 watts multiplied by 1 hour. In other words, it's 1,000 joules per second multiplied by 3,600 seconds. A kilowatt hour is 3.6 million joules. So a kilowatt hour is an expression of energy. And of course, energy we have to pay for, right? Whether it's in the form of electricity or the stored energy in our gasoline, energy has a value to it, and we can always calculate energy by multiplying power times time. So I want to show you how you can calculate electrical power. Again, we'll refer back to the conduction of electricity through a metal wire. We'll say there's one of our free charge carriers. So there's a total amount of charge, but if we just pick one of them, it represents just a little bit of electric charge that's going to drift from the high potential to the low potential. Now, just to make life easy for ourselves, let's imagine it's a positive charge carrier. So the drift speed and the current are in the same direction. Work is equal to force times distance. If the charge started all the way on the left end of the wire at point A and drifts to point B, then it's drifted a distance of L, and the force is QE. Well, I guess dQ times E is the force. Power is the rate at which work is performed. It's a rate of change of energy or rate of work done. So let's see. dW dt, the rate would be dQ dt. I'm just going to divide both sides of this equation by dt. And then we're still left with E times L. But wait a minute, E times L, if I multiply the electric field inside of the wire times the length of the wire, that's just the potential difference across the wire. This is just the voltage. And clearly dQ dt is current. Oh, so there we have it. Power in an electrical conductor is nothing more than the product of the current and the voltage. Let's double check that. Current is measured in coulombs per second. Volts are the same thing as joules per coulomb. Well, yeah, certainly. We're left with joules per second, and that's a watt. So power is the product of current and voltage. But then again, there's a relationship between voltage, current, and resistance. So we could substitute, in place of current, we can substitute V over R. So we could say power is equal to V over R times V, or in other words, it's V squared over R. I guess we could have just as well substituted away for voltage. If we were to do that, we'd substitute voltage with the product of current and resistance. So we can say P is I times IR, or in other words, P is I squared times R. So there are three equations that we could use to calculate power, just depending on which of the three quantities out of V, I, and R we happen to know. We either say P equals IV, P equals V squared over R, or P equals I squared times R. Keep that in mind.